Thank you very much. First, I have to say that I'm sorry for the Professor Kevin and everybody for the late and due to the trouble connecting Zoom. I'm sorry. And I'm very happy to present about um, these titles. And our group has been developing the superconducting motor system for the transportation equipment such as the ships and the automobiles. And we wanted to apply to the middle-sized passenger car. Okay, this is the contents. My talk. First, I wanted to quickly explain about the background, and then the rotating mechanism of our motor. It's called the HTS-ISM. It's abbreviation for the high temperature superconducting induction synchronous motor. And quickly review the R&D history of our development of the 20 kilowatt plus prototype motor. And we have just completed the development of a 50 kilowatt plus motor motor. And we are now moving on to the development of 100 kilowatt and more output motors. So I wanted to explain about the present status of the 100 kilowatt. Okay, final target is the image of it's a drive system like this. And this is shaft and the rotor is this lotus. And stated directly coupled with the core stage of the cryocooler. And this is the compress of the cryocooler. And our history development of superconducting module is started from the 2005. First, we start with the several kilowatt or even 10 kilowatt motors. And gradually we developed and larger size motors. And we are now around here and just completed the development of the 50 kilowatt plus motors. And just now from now, we are now moving on to the practical development of the several 100 kilowatt fully superconducting motor. This is first of all, quickly, I wanted to explain about the rotating mechanism of our motors. This is the schematic diagram of our motors. And actually, this structure of this motor is the same as that of the simple structure squirrel cage induction motor. And from this rotors, we can extract the the second winding like this. This is called the squirrel cage winding. And our primary motivation is the replacement of this winding with use of the HS wires. So by using the HS wire to the this winding, thanks to the zero resistance of the HS wires, we can show the shielding current is the flowing in this winding. So this because the magnetic pole is equivalent to the form in practice. So in this case, even the structure of this motor is squirrel-cage induction motors. But you can realize the highly efficient synchronous operation thanks to the HS protocol. And more detailed explanation of the motor is like this. This rotation is, we just consider the one loop of the HTS squirrel-cage motors. This is a rotor burst and blue one at the end rings. And both of them consist of the superconducting wires. So superconducting wire has the this kind of nonlinear resist electric field by the current curves. And firstly, when the magnetic field is applied to winding, because of the shielding current of these rod windings, and this magnetic field is shielded from the this winding. So in this case, unfortunately, the rotor cannot start rotating. And by increasing the rotating magnetic field, corresponding current increases. And when this current is overcome the critical current, this winding, the flux can be interlinked to the winding thanks to the flux flow resistance. And at this moment, the rotor starts rotating. And then we just wait for the rotation. In this case, the rotor starts rotating and then accelerating, and the corresponding current going back to the smaller part. And when the current in the below its critical values, such a flux is trapped in the winding. So equivalent magnetic pole is formed here thanks to the passes current. So synchronous rotation available. So originality of a motor is not only the zero resistance, but also the nonlinear current transport property. I mean, flux flow state of the scale one is effectively utilized as floating mechanism. This is electrified by the current curve and corresponding torque versus rotation speed curve. So our motor has both of the synchronous torque and also slip torque at the overload conditions. So the simple torque corresponds to this state, and the slip corresponds to flux flow state. And based on the fundamental characteristics, we have already completed the 20 kilowatt class prototype. And this is a BISCO wire, BISCO 222 wires for the rotor winding, and it's coupled to the with the capacitors, and the various kind of test is carried out. And this is the main voltage assembly. This one installed inside of the liquid nitrogen cryostat. And it's already reported that, for example, we realize the load cap. This is synchronous speed, and successfully realize the unsynchronous rated power with the 20 kilowatt as designed. And when applied the overload, double, I mean, more than 40 kilowatt overload slip power is also available. And we also get the maximum efficiency counters. This is very small, 20 kilowatt, and also capacitor utilized, not the superconducting data, but you can already realize more than 97.2% at this condition. And of course, the variable speed controllability is very good. And also, we have recently completed development of 50 kilowatt module motor. First, again, BISCO rotor is coupled with the conventional capacitor and this assembly, and the various kind of tests is carried out. And for example, this is the typical rotor test. This axis is the output and the rotation speed, and the synchronous rotation speed at this case is the 1050 RPM. And of course, we can realize the 50 kilowatt and also overload slip operations at 64.7 kilowatt is available. And also in this case, we carry out many times the load test with the various kinds of input voltage, and we get the maximum efficiency like this. This is a typical result for the rotation speed 1000 and 200 RPM. And this moment, the maximum efficiency reaches to the 99.4%, even the capacitor still is utilized. So we are moving on to the development of fully superconducting motors. And we use the same BISCO rotors, and at this case, in this case, the BISCO stator is utilized. In this case, a little bit special structure. It's called the toroidal structure stator utilized in order to push up the critical current of the stator winding. And this is the assembly. And this is also already reported, but we succeeded with the fully superconducting 50 motors with the load test with the 39 kilowatt. And also right load variable speed control test is also succeeded. So, and based on such small scale motors, we are now moving on to the 100 practical side, 100 kilowatt plus motors. Actually, we use the same 50 kilowatt fully superconducting motors, and simply changing the number of stator turns from 12 to 16. Not so big changes, but we can realize 500 Newton meters. Actually, corresponding our power already reaches the 100 kilowatts at this condition. So already with the use of a 50 kilowatt motor size, and we can realize 100 kilowatt. And also, we are moving on to the another type of 150 kilowatt plus motors. And in order to do that, actually, we are very careful about treating the superconducting properties of superconducting rotor bus. And in order to characterize the superconducting rotor bus nonlinear characteristics, we adapted to typically utilize the Kim Anderson modules for the critical current for the parallel directions and the this is the parallel direction, perpendicular directions, and this one to parallel direction, perpendicular direction, N value. And by fitting the manufacturer data by using the Kim Anderson models, we can get the good argument. This kind of curve is introduced into the electromagnetic field analysis code. So by using such characteristics, we can realize the exact shielding, nonlinear eddy current characteristics inside of the rotor bars. This is very important for designing the high power superconducting and HTS ISM. So finally, we can get the 150 kilowatt motors. Actually, this one the low speed value, so a corresponding torque is very high. It reaches the 2,865 Newton meter at the 500 RPM. It's possible for the very small size volume. So based on this analysis, we are moving on to the publication of this model for the middle-sized passenger craft with the company. Okay, I would like to summarize my talk and around the history of the HSIS and Kyoto University is reviewed and discussed. I will review that when the number of the stated turns of the 50 kilowatt class fully superconducting motor is simply changed from the 12 to 16, and out of the already 100 kilowatt it realized. And also 150 kilowatt class practical size for the passenger car HSISM has been designed. And we were moving on to publicate with the company. Future plan and the Biotra and the R&D expand the HSIS, and we are promoting large corporate joint project of EVs, not only EVs, but also SIPs and the liquid hydrogen transport pumps. Thank you very much for your attention.
Thank you.